All right, welcome back everyone from lunch. Hope you all had a good time and stayed cool. We're going to start off this next session with an invited talk from Phil Hopkins from here at Caltech, who's going to talk about Roman and some big unsolved problems in galaxy formation from a simulation perspective.
All right, thanks everyone. So since it's right after lunch and we're all tired, I'll try and include a bunch of movies to entertain everybody. So this is a highly biased review of, from the theory point of view, what I think are a few of the biggest unsolved problems that drive a lot of our theoretical uncertainties in modeling galaxy formation. And there was a lot of arbitrariness in how I chose the problems I wanted to focus on in this talk. So there's things that I think are huge uncertainties, but maybe are more an uncertainty in star formation that also ripples into galaxy formation. So I really debated, for example, including the IMF and stellar multiplicity and the effects of massive stellar evolution here, because they do ripple into galaxy formation, but I decided that's a star formation or stars problem. So I'm keeping this to sort of galaxy questions, and I'm going to just hit on a few areas that I think are really driving a lot of the uncertainties in the field. So the first topic area I wanted to mention is the effect of cosmic rays. So we haven't had much discussion on this so far in this meeting, but this has become a really big subject if you go to galaxy formation conferences, especially about the theory and simulations. So we know that in the interstellar medium, cosmic rays are sort of in equipartition with other energies like turbulent and magnetic and radiation and thermal energy densities, and they come from both acceleration in supernova ejecta and AGN jets, with definitely open, interesting physics in how they get there. And there's been a growth of different ways to study them, and actually a remarkable convergence, I would say. It's not, the details of this plot aren't important, but there's been a tremendous amount of convergence actually from different modeling efforts in our understanding of cosmic rays within our galaxy, and specifically within the immediate neighborhood of the sun, things that we can detect with, terrestrial or International Space Station or Voyager type experiments where we're actually directly measuring cosmic rays. You can measure the spectrum of all these different species. We know that most of the energy is in these sort of GeV, mildly relativistic protons, and this has given us a lot of understanding of their transport. But one thing that's been emerging from this, just empirically, is that cosmic ray weather or inhomogeneous transport really matters. So often when we talk about cosmic rays, one of the big theoretical uncertainties is not, where is most of the energy in cosmic rays? It's in GeV protons, probably. It's not how much energy from feedback goes into cosmic rays. It's, at least from stars and supernova, that's not so uncertain. It's 10% roughly of the kinetic energy of supernova explosions. AGN, that's more uncertain. It's how do they travel through the galaxy to get places, and how does that diffusion coefficient or streaming speed, or however you want to parameterize it, modulate. And we know already just within our galaxy that there's growing evidence. So this is work by Irina Butsky, this is work by Margot Fitz-Axon showing ionization statistics in different molecular clouds in the galaxy. Work by Isabel Sands has been exploring things like gamma ray maps of the galaxy, the Fermi bubbles, the galactic center excess. These things are all subject to what you'd call cosmic ray weather, meaning inhomogeneities in the ISM that strongly affect not just the rate at which cosmic rays lose energy, because that depends on things like the local radiation field or the magnetic energy density of the ISM, but also the plasma physics of how cosmic rays are interacting with magnetic fields. And unfortunately for these cosmic rays that have most of the energy, that's happening on sub-AU scales. So what we care about are resonant plasma physics interactions happening on about 1/10 of an AU scale, integrated over kiloparsec scales, for whether or not you do things like trap enough cosmic rays to launch a wind. There's plenty of energy in there to do that, but whether you do it depends on those microphysics. And as a result, for different plausible physics assumptions, this is cosmological simulations of a Milky Way-like, Milky Way mass galaxy halo run to redshift 0. This is a map of the temperature of the circumgalactic medium in the ISM, and these are inflows and outflows on a megaparsec scale. So this is a simulation where cosmic rays do nothing, because they get out of the galaxy, which we know they sort of need to be doing. Most of the cosmic ray energy is leaking out of our galaxy, and then they just couple very weakly to the circumgalactic medium, and they just fly out and do nothing. And what you see is that matter is accreting onto, this is the virial shock here, onto the galaxy, and it's fairly hot inside the virial radius, virialized gas. Whereas an alternative model that's also perfectly physically plausible is that those cosmic rays are not able to leak out of the circumgalactic medium, their travel times are too long, and so you build up this reservoir of cosmic ray pressure in the circumgalactic medium. It supports cool gas that would otherwise rain out onto the galaxy, so you have a completely different temperature structure of the circumgalactic medium, and you support these slow, biconical, highly ordered winds that travel out to megaparsec scales. And again, from a theory point of view, I honestly cannot tell you which of these I favor a priori. I think this one's more interesting. And I have observational arguments, I think, that are starting to come together about this. And one of the things that people have been starting to look at, this is advertising some work by grad students here, Sam Panada, former student, and Emily Silich. People are starting to look at things like X-ray diagnostics of the circumgalactic medium from Rosita and other missions, and finding that there's maybe extended X-ray emission that could come from inverse Compton scattering, that there's SZ effects, that there's other interesting effects. But the reason I'm bringing it up here for Roman is that this also affects things like the macroscopic distribution of matter. It affects galaxies very strongly through how massive they are, how they blow winds, how effectively gas collapses and forms stars, but it also can affect this larger scale matter distribution. We just had a talk before the break about this S8 tension and the fact that the baryons seem to be pushed out at megaparsec scales from galaxies around group mass halos, right? And one of the interesting things about this is that if you look at, for example, simulations that are calibrated to match the X-ray observables, they are forced to lie in some envelope here. Weaker feedback is often how these simulations are referred to. They don't have strong enough feedback to push things out. And the reason this is really important to think of in the context of cosmic rays, so you might say, well, cosmic rays could leak out and push things down this way, but it's not just that cosmic rays act like another mechanism of feedback, because the physics are fundamentally different. If you want to push things out with thermal feedback, with mechanical feedback, if you model supernova as some combination of heating and punching the gas, then you either are forced to very large velocities of outflows here, or you're forced to very high thermal pressures here. Which means that if you take a signal like this that might be inferred from something like weak lensing, and cross-correlate it with signals that we get from other cosmological probes from, say, the Sunyaev-Zeldovich effect, thermal or kinetic, the vector direction that you move in that plane from any type of mechanical thermal plus kinetic feedback model is actually almost orthogonal to the vector direction you move in that plane if you amp up the cosmic ray pressure. Because the cosmic ray pressure will actually, if you crank up the cosmic ray pressure, I'll actually get cooler gas here, I'll lower the thermal pressure vector, and I'll get slower outflows. So my SZ and my T and KSZ effects will go in the opposite direction from how they would go if I crank up the sort of traditional mechanical feedback. And this is important because when people have modeled this, the overwhelming modeling of this is taking simulation suites like flamingos or camels that vary a bunch of their feedback parameters, but the point is those are hydrodynamic simulations. There is no parameter in flamingos that can move things along that vector. So in other words, if we think of the galaxy formation space as some high-dimensional hyperspace with a bunch of different things happening in it, our current big simulation libraries sample a sheet in that hyperspace, basically, and only a sheet. And if nature lies off of that sheet, then your fancy, machine learning model to project onto and emulate those parameters is going to break or just going to give you unphysical answers. And so I'm not saying that this is what's happening in nature, just that we need to think about it. And there's work by a student at Caltech, Isaac Cheng, trying to make new sets of models that span some of these other physics. So, all right. I had too many slides here about cosmic rays because I love them. But what's another big uncertainty? Well, one that we have heard a lot more about that is related, all of these tie together at some level, or could be related, is bursty star formation. Right? So there's been a lot of literature on this. This is just a subset of some of the literature, mostly a few years old or older, of how much bursty star formation affects galaxies. And from the theory side, there's been a robust emergence of this sort of multi-stage picture of galaxy formation. This was a cosmological simulation sped up where you have this early chaotic, messy phase. I'll play it again just so you can see it, where things are collapsing very rapidly. You have starbursts, you have a lot of infrared interesting activity, and then you have things settling down as the pace of accretion onto galaxies and mergers, and therefore feedback also drops. Things settle, and you finally, only at late times for a Milky Way mass galaxy, start to settle into the textbook picture of galaxy formation. You were probably taught gas collapses onto a halo, shock heats to the virial temperature, cools, conserving angular momentum, and spins up into a disk. That happens here, but at Z of less than 0.7. Everything before then is described by some chaotic, clumpy, messy mess. And you can still get beautiful, nice, thin disk galaxies, but you have this sort of, striking transition of star formation behavior that's also correlated with morphological structure in galaxies. You build up things like the thick disk. This is the sort of, inside out and upside down picture of galaxy formation. That things like the thick disks are not born razor thin and then kinematically heated. Kinematic heating happens, but thick disks are born thick. And then they can get heated again on top of that. This also has big implications for things like our understanding of galaxy kinematics and dark matter and rotation curves and all of that. This is an example by Isabel Sands of showing some numerical simulations where this black thick line is what we usually compare when we model rotation curves of galaxies. This is the theorist's rotation curve. This is square root GM over R enclosed in the galaxy. This green line is what you would measure if you take put a slit along this dwarf galaxy and then feed that into your favorite tilted ring model to model out the kinematics of the galaxy and infer a GM over R. And this gray point is just one particularly weird observed dwarf galaxy. And this is just saying that, fundamentally, why is this so different? It's simply because the most foundational assumption that we make when we do this kind of galaxy kinematic modeling, that galaxies are in equilibrium, right? That I can drop the time-dependent terms and treat A equals B as some kind of steady state, is just wrong for these bursty galaxies during this stage. It's not really until you get to this settling stage that that assumption is valid anymore. So this has really big implications for a lot of things. There's also work by Jacob Shen and many others, and Jason Sun, who's in the audience, showing that there's been a lot of work on how this could potentially explain these high redshift, anomalous, bright populations of galaxies. And this is just a sort of heuristic diagram of your JWST UV luminosity function, where at first everybody was freaking out because there were these super UV bright things, and we said, oh, our reference model is nothing anywhere near that bright. And then you say, okay, well, the models actually predict that star formation is more efficient in dense halos at high redshift. You can get things like observational biases. Oh, there's also lower metallicity, so they're a little brighter in the UV. You might have some AGN contamination at the bright end. But a really huge effect that Jason and Jacob pointed out and got people really talking about is that if you have these bursty, highly fluctuating star formation rates, it strongly biases you in the UV. But of course, the effects are much weaker in something like the IR, and at lower redshifts, we're not as subject to this, both because we're looking at longer rest frame wavelengths, but also because galaxies have more reached these calmer phases, and they're less dominated by the youngest, most recent bursts of star formation. And this is just from their paper, is showing this really does make a quantitative difference. And this ripples into a host of other things. We also heard about black holes sinking, and it's even worse than we heard in the last talk, because I'm just pointing out some work a few years ago by Lin Hao Ma, but there's many people who've pointed out the same phenomenon. When you have this bursty, clumpy phase, if you want to have a black hole sink to the center of a galaxy, or even stay in a galaxy to be able to accrete efficiently and shine as an AGN, let alone merge to be a LISA source, good luck. When you're in that explodey, clumpy, messy phase, dynamical friction doesn't work as a phenomenon in that stage. You get ping-ponged around. You're just dynamically being scattered by macroscopic n-body heating from all these clumps and star clusters and mass and dynamical perturbations. It's violent relaxation happening. You have a time-dependent gravitational potential. At the late times, this is some simulations by Daniel Anglès-Alcazar. You see this was just targeting the most massive black hole. These dots were the black holes. It sort of settles into the center once you start forming an ordered galaxy. So when and where this happens for different galaxy types ties very strongly to their black hole properties and all the things that come with those black hole properties, basically. And honestly, we still don't even fully understand. There's very active research continuing. Folks like Jacob, also Vadim Semenov has written an excellent series of papers on even how this happens, even in the simulations. We don't fully understand what leverages this transition from bursty to calm. We actually are still arguing amongst ourselves, even in our own simulations. It's such a complex, nonlinear process that you can't really isolate one mechanism trivially, and you can make different combinations. So usually we see, and we often talk about burstiness going hand in hand with sort of messy morphologies, but you can make, this is a little hard to read, but the point of this is these are simulations illustrating that it is possible, if you mess with the physics in different ways, to make galaxies that are bursty and non-disky, to make galaxies that have very smooth star formation histories, but are still a complete morphological mess or smeared or non-disky. You can make a disky galaxy with a bursty star formation history, or you can make a disky galaxy with a very calm star formation history. So getting to the bottom of this is going to take a lot more work. This is just, I'll skip this, but this is sort of a summary slide showing that there's some theoretical consensus that as galaxies get more massive, the potential wells deepen, it's harder for feedback to blow them up. And everybody kind of agrees qualitatively it's something along that line. But really where and when this happens in nature, because it's so sensitive to those feedback details, is going to be an observational question more than a theoretical question, I think, but informs so much of these other things we do. All right, since I'm already talking about black holes, I'll spend a little less time on this, but another thing that's come up that we really have a poor understanding of is the seeds and the very early growth of supermassive black holes. And this obviously ties to all these questions about little red dots and high redshift AGN and the early growth phases and the seeds. And again, we've already heard people talk nicely in previous talks about these different classes of models. Could you have hyper-Eddington accretion, where you have bursts of very high Eddington ratio? Could you have things like direct collapse of gas clouds? Could you have things like runaway mergers of stars in the centers of dark clusters? Could you have exotic physics mechanisms like certain dark matter models can run away and collapse? And I'll come back to the dark matter questions in a moment. All of these are viable. Now, some of these might end up looking very similar in the end. So a generic picture, if you know this field, you'll see in what I'm about to show you, I'm going to encode my biases. But parts of this are very generic in all of these pictures. So the idea is you have some dense, you have some gas cloud. In the low redshift universe in most galaxies, excepting maybe dense nearby starbursts, most of these clouds are pretty low density. And so what happens when you have a self-gravitating but not very dense gas cloud? You turn a few percent of its mass into stars and it blows itself up from feedback from those stars. That's the usual path for anything in the Milky Way, for example. Those are pretty puny, 100 solar masses per square parsec or so densities. But let's say you have a really dense gas cloud like we see at the centers of starburst galaxies or in high redshift galaxy clumps, 10 to the 4, 10 to the 5 solar masses per square parsec of gas. Well, then it's a completely different evolutionary track. It starts to collapse. Its gravitational potential and acceleration scale are so deep that young stellar massive star feedback can't blow up the cloud until it eats almost all of the gas into stars. So you form a very massive bound star cluster. This is widely accepted as the way that you form bound star clusters and the progenitors of globular clusters. But if you have some mechanism to generate black holes, this is also the sort of ideal mechanism to grow your seed black holes. And it doesn't really matter, maybe if all you care about is the end product, how you do it. There's sort of three branches people talk about. One option is if somehow you have just the right irradiation in a metal-free cloud, this whole cloud could collapse homologously into one supermassive star that then undergoes this GR collapse to a black hole. That's direct collapse. Then you get this whole cloud, skips the stars, goes straight to black hole. Another option, though, is that it does fragment into stars, but the central stellar density is so high that those massive stars start sinking into the center and merging with each other before the end of their main sequence lifetime. And that's also completely plausible for the densities of the massive, dense nuclear star clusters that we see today, and the densities of these things. And so then you would either build a massive black hole that eats runaway stars or a supermassive star again from the mergers of these, depending on exactly how quickly the core of that thing collapses and how much mass it loses to winds. And then the other branch is that maybe they turn into stars. The stars aren't able to merge quite quickly enough or have too much mass loss to build up a supermassive thing by mergers, but you have some 10 to 100 solar mass black holes floating around, which you will in a massive cluster of this size. And those things, some of them, some small fraction, will get lucky and hit some dense clump of gas that they'll run away, accrete in an incredibly short amount of time, and you'll have a short-lived burst in these simulations by Yanlong Shi. In 100,000 years, this black hole accreted 100,000 solar masses worth of gas. It was on at 1,000 times Eddington, but it only needs to be on at 1,000. If you want to ask how long, what's the E-folding time for a black hole to grow? At Eddington, it's a few tens of millions of years. At 1,000 times Eddington, you just divide that by 1,000, right? That's a few 10,000 years, right? So you can grow by orders of magnitude in less than a million years very easily, and that's another scenario. So all of these things can happen. Maybe all of them do. But I would say that regardless of the details, if you see the theorists arguing with each other, there's actually been a lot of convergence among the theorists that it's something like this kind of environment, and then we're arguing about what exactly happened in these couple stages inside the cluster. But if we can nail down whether that's the story, like are these things born in these dense natal cloud and star cluster environments? Do they grow super rapidly? I think we'll be a lot further towards understanding the sort of seeds that ultimately form the supermassive black holes and galaxy centers. This is just because I'm overdue for showing you a very pretty movie. The work on the theory side has continued to progress to try and model this whole dynamic range of scales. This is just some fun simulations we've been doing as we start thinking about going from the growth of black holes to AGN feedback, which is another big unsolved question. We've already heard again about this, what AGN do to their galaxies. And to model this is very challenging because to do it right, without putting in just some guess about what's coming out from the AGN, you need to put in a whole mess of physics, and you need to model some huge dynamic range of scales, because you need to model the gas going down into the black hole, but also most of the radiation, the jets, the winds out of the accretion disk are being generated at these scales of order a tiny fraction of a parsec, maybe hundreds of Schwarzschild radii from the black hole, and you want to follow them back out to parsec scales. Sorry, the movie gets very choppy. But this is starting to become possible in numerical simulations, but it's still leaving a lot of open questions. We know that AGN feedback needs to happen, and we see plenty of examples of AGN feedback happening, but we're still trying to figure out how important it is for galaxies and where and when the important parts of AGN feedback happen. And from the theory point of view, what I would say is one of the biggest questions is, of the different mechanisms of AGN feedback we know exist, which matter where and why and how? I don't think it's just that one of them matters, period, but we know there's things like relativistic jets, right, coming out of these small scales. And we know there's things like radiation. You can have radiation pressure, ionization, Compton heating, launching winds, heating up gas. We know there's things like non-relativistic winds coming out of accretion disk scales, propagating out to as much as KPC scales in galaxies. And we know there's cosmic rays being accelerated. We see, powerful leptonic sources, synchrotron, gamma rays, et cetera, coming from these systems. So we know that they're accelerating relativistic particles. So all of this is happening, and I think as the models get better, they start making more and more interesting predictions, because it used to be you lumped all of this into your AGN feedback banner, and you just assigned one number. You said there's an efficiency. There's a fraction of MC squared that comes out. And it comes out in whatever the simplest numerical thing I can do in my simulation is, which for my PhD was the dump it all in thermal energy in the nearest 32 cells around the black hole, right? But we're now getting the capability to actually model, all of these things obey different physical equations, right? So they have different effects on galaxies. And we can start doing that and doing things like cross-comparing the effects on the quenched galaxy population to, for example, the demographics of different types of AGNs that would be active in different ways here. Last is perhaps the most uncertain of all of these, what the heck's going on with dark matter in all of these galaxies. Good news, bad news, this is what I show my cosmology class. This is a plot of all the possible particle masses that the dark matter particle could have, from left to right, top to bottom, going from the dark matter is so light that its de Broglie wavelength fills the entire horizon of the universe, the Hubble volume, to the dark matter particle is so massive that all the mass in the universe is in one dark matter particle. Colored is ruled out, so you're not surprised to find out that the fact that the rest of the universe exists means that this is ruled out. This is mostly the PBH range. We heard about there's some windows that might hide in, but whoops. I don't know what just happened. Here we go. There's our sort of, when people talk about fuzzy dark matter or ultralight dark matter, that's this sort of stuff up here. The good news, bad news. Good news is, if dark matter only interacts via gravity, we have done the astonishingly impressive job of ruling out 50 orders of magnitude of parameter space at this point in astronomy that the dark matter particle could live. Bad news is there's still about 50 orders of magnitude left that it could live and be perfectly compatible with all the observations. But I think one thing I want to make the point of is that the models are getting more sophisticated. There's been an explosion of work to incorporate different realistic particle physics dark matter models into cosmological and galaxy formation simulations and predict their observable effects on galaxy demographics. And it's not that dark matter is simple by default in our simulations because we actually think dark matter has to be simple, either observationally or theoretically. It's because simple is simple, and I'd rather do something simple than something complicated. So we say dark matter is collisionless and only interacts via gravity, not because there's a good reason that has to be true, but because that's the simplest thing for me to simulate. And some old tensions have, of course, gone away. I think it's probably not a surprise to tell people here that nobody who's seriously working on this, I would argue, thinks that, for example, the missing satellites problem is a problem. You just have low efficiency of forming stars in tiny dark matter halos. But one interesting result that has emerged is that if anything in the universe, so we can reproduce lots of different morphological types. This is just an excuse for pretty pictures. There's all this debate about small-scale structure on kiloparsec scales. Can we get cusps and cores? Can we get the diversity? There's this so-called diversity problem. There's things like planes of satellites. All these things that maybe suggest that there's a shortcoming in the dark matter on KPC scales. But of course, everybody here should already be aware these are very degenerate with the baryonic uncertainties in modeling, and we need more observations to disentangle them. I already gave warning lessons about these rotation curve interpretations. But one thing that I think outside of people who really work on testing particle dark matter models is not widely appreciated in the rest of the community is that for decades, I think this community was obsessed with the idea that we need dark matter to be fluffier. The universe is somehow much less dense than cold dark matter predicts. And that's your missing satellites problem, your cusp core problem, a lot of these other, Tully-Fisher problem, etc. But things have actually shifted. The consensus now is that most of that was because we were doing a bad job modeling feedback. And actually the things that have proven harder and harder to reproduce in the modern universe are dense, compact things. If anything, from some recent lensing studies, from galaxy morphologies, from a number of surveys of structure on small scales, there are hints that maybe, and I'm not going to bet money on this if you ask me to, the dark matter model has more structure on small scales than cold dark matter, the vanilla cold dark matter predicts. So if anything, we've been maybe smelling in the wrong direction, and we really need new constraints to think better about this. And I'll leave with another movie. Thank you very much.
All right, thank you very much. We have time for questions. Can we get there? We can start here and then there. Yeah, middle. Mm-hmm. Yeah, cool. Thank you.
Hey Phil, great talk. I actually have two questions, but you can answer either one. I guess my first question is that there's been quite a lot of discussion about these like turbulent mixing layers and you need like ridiculous high resolution to capture that. Yeah. And apparently that's like a real factor in capturing the cooling, and that probably affects like thermal momentum feedback and stuff, which I assume is still not yet captured in fire. So I'm wondering if you have any thoughts about that, and if that might lead to over underestimates of like the importance of cosmic ray feedback. So that's the first question. And then second question is, do you have predictions for how we can see evidence of bursty star formation in like redshift 0 galaxies? Because I assume like all the ultraviolet objects are gone, so you're left with the stellar disk. So.
Yeah. So to answer your first question, I completely agree. There's a lot of microphysics that are still not being captured, small-scale physics that aren't being captured in these simulations yet. And as always, people are trying to improve the sort of subgrid models for the things that are not possible to resolve. People are doing, super high dynamic range, zoom in on a patch of the CGM, but then you can't do that everywhere all the time. So you have to use that to inform models. And that will correct the sort of effective cooling rates and clumping and a lot of things. And it will definitely interact with your inferences about cosmic rays. That said, it's also, I wouldn't say it's strictly degenerate, because there's still this question of moving along potentially independent axes here. And cosmic rays do affect that. There's a couple really interesting papers by Timon Thomas, as well as Irina Butsky and others that have shown in very high resolution simulations of those mixing layers, if you dial up or dial down the cosmic ray to thermal pressure ratio, you can do things that are really wild. Like you can qualitatively change the character of the thermal instability. You just get different instabilities. So I think it's more that's another dimension we need to think about the uncertainties along and try and parameterize in some effective way. To your second question, now I've gone and forgot your second question. I'm sorry. Oh, yes. So there's, you said, so if we have UV, people have tried to look at like UV to optical ratios and diagnostics of star formation on different time scales. If you don't have that information, I think there is still information, especially if what you care about from the bursty star formation point of view is it perturbing things like the orbits of stars, because that actually does leave an imprint on morphologies, on the gradients in galaxies, like the metallicity gradients and the age gradients in galaxies, the color gradients get mixed up, because if you're churning it around to make a core, there's no way to avoid kicking the stars if you're kicking the dark matter around. So there is a correlation predicted there that I think we can test.
All right, we can go over there in the back.
Thanks for the very nice talk. So I have a question about the seeding black holes and the evolution to the little red dots. So no matter whether it's direct collapse black hole or the runaway process, I suppose those seed black holes cannot form in like random halos, right? So my question is, what's your expectation about the halo mass of this kind of seedings, and what's their duty cycle or lifetime before they evolve into the like regular regime?
Yeah, so I think this is something that there's still a lot of active work to really figure out when these things happen, what's happening on small scales. And again, it's a huge dynamic range of scales you want to resolve, because to really resolve the accretion, you need sort of sub-AU resolution. So again, people are combining hybrid approaches right now to do that. And the answer will depend on which of these channels it does take. So for example, if you really do want to get the direct collapse scenario where you have the whole cloud collapse, there's a couple of claims contrary, but I think most people still think you need a metal-free or nearly metal-free cloud that's externally irradiated by a Lyman-Werner background. So that sets very specific environmental constraints on where that can happen. If, on the other hand, you're happy to let the cloud fragment and then runaway merge or runaway accrete onto a black hole, then actually your preferred environment is more the deepest potential well that this can happen in, where it's still interesting for this to be a seed. So more evolved galaxies a little later, maybe in cosmic time, not talking, redshift 1 massive halos, but talking maybe, the difference between a redshift 30 mini halo and a redshift 7, LMC mass halo or something like that might be or at least atomic cooling halo might be the difference. But again, I think it's really something we're trying to quantify right now.
All right, there are a few more questions, but we'll move on so you can ask them during the coffee break.
Thank you.
Yeah, we'll thank Phil again.